Lecture today is, as you can see, is entitled Variation of Parameters. This is one method of, or yet another method of finding a particular solution for a linear, non-homogeneous, and, well, in particular, second-order linear equation. So while I guess a lot of these methods can be generalized to higher dimensions, we're only really going to focus on the second order case. I think I've said something like that previously. However, this particular method, the variation of parameters, is a little bit more difficult to generalize. So we'll really focus on the second order case here. So I'll just remind you what that's referring to. So we're mainly interested in finding the general solution of this equation that I'm pointing to here. So this second order linear non-homogeneous ODE. Okay, it's non-homogeneous because we assume that this function on the right-hand side is, well, it's something non-zero. Okay, and what's more, we know the general solution comprises two parts. One is this complementary function or homogeneous solution, which I've been referring to as YH, and the other is the particular solution. So it's the YH part of the general solution that contains all of the arbitrary coefficients, right? That's part of that forms the general solution. Okay, and it's once we have this general solution that we can then impose any initial conditions. But it's that particular solution, the YP part of the general solution, that contributes to the non-zero right-hand side. What we saw last time was the method of undetermined coefficients, so-called because we have a look at the form of the right-hand side, and depending on what that is, we make an educated guess to the form of the particular solution. All right, and we solve for the undetermined coefficients. So I'll just remind you that method, what it came down to was just a simple matter of substituting a good guess into the left-hand side of the differential equation and then setting it equal to the right-hand side, and the process of finding the particular solution then just becomes a matter of solving a couple of equations in the coefficients, right? Very easy to do in comparison to some of the other, well, you can't really compare, but some of the other first order methods that we've seen, right? Remember, some of those other methods, we reduce the problem of solving the differential equation to having to evaluate a couple of integrals. Generally speaking, solving some algebraic equations, and they always end up being linear in those undetermined coefficients. Solving some algebraic equations is generally a lot easier than evaluating integrals. All right? Now, the only problem with the method of undetermined coefficients is that it only works for constant coefficients that appear on the left-hand side of this equation when it's written in standard form. Standard form, I mean, put all the unknown, all terms involving the unknown function y and its derivatives to the left, and to the right is just a function of x. Okay, so in the case where p and q, those coefficients are constants, and in the case where r is either a polynomial, exponential, cosine or sine function, or actually a product of exponentials and cosine or sine functions. So we looked at those in the last lecture. In that case, we can make an educated guess of the form of the particular solution. And that was just based on some observations I made, that if you plug in a polynomial to the left-hand side of that equation with constant coefficients, out comes a polynomial, and so on. All right? Now, what happens when the right-hand side is not of that nice, not one of those nice forms, right? What happens when it's not a polynomial or cosine or sine function or exponential? What happens if it's a lot more complicated than that? Well, that's where this method that we're going to look at today, the variation of parameters, comes in useful. All right, it's actually a variant on, or the way I'll present it here today is a variant on something you're already familiar with. I think reduction of order you've seen before. I've mentioned it in the last lecture. So that's where you have a solution of, well, in this case we're talking about non-homogeneous equations. If you have a solution of a homogeneous equation and then you set the solution that you're looking for equal to some function u times the solution that you have, and then you determine that new solution. That's reduction of order. You end up reducing the order of the differential equation in that unknown function u that you introduce. It's a little bit like that method, but well, but slightly different. So what I've got, or the way I presented the discussion here is just to state the result up front, just tell you what the result is, and then we'll have a close look at the details and then look at some examples. So the main idea of this lecture is, or the purpose of this lecture is to present an alternative method of solution for these particular solutions that occur in the general solution. So that's what we're all about, finding the particular solution in this case. So I guess the outline of the process is just in these dot points here. The first point is we'll assume we have a solution to the corresponding homogeneous equation. Now really the only solid method you've seen for solving such homogeneous equations is in the case where there are constant coefficients, so where p and q are constant. Now in assignment 1, question 3 I think it is, that second order linear non-homogeneous differential equation that I get you to solve, that is I get you to find the general solution, I actually give a hint where I give you one solution of the corresponding homogeneous equation. So when I give you a solution like that, that's a bit of a hint that you could use reduction of order to find the general solution. But nevertheless, this is yet an alternative way of doing it. So we're going to assume we have we know the general solution to the corresponding homogeneous equation. All right, so the way it's worded here is, it says we solve this to obtain a basis of solutions, y1 and y2. Because it's second order, we know from the theory that we should have two linearly independent solutions. All right, if it was a sixth order equation, then we know to write down the general solution, we'd need 6 linearly independent solutions. It's very easy to determine whether or not two given functions are linearly independent simply by taking their ratio and seeing if it's a constant. If the ratio is a constant, clearly one is a multiple of the other, right? And so then they're not essentially different, or in other words, linearly independent. Okay, so that's what we do to start with, is work out the linearly independent solutions, y1 and y2. And then we introduce this quantity w, which is known as the Wronskian of solutions. I'll just point out that the Wronskian as defined here is actually the determinant of a 2 by 2 matrix. So in the first row, we can place the solutions y1 and y2, and in the second row we can place the corresponding first order derivatives, so y1 dash and y2 dash. So if you take the determinant of a 2 by 2 matrix, that's just the product of the entries on the diagonal minus the products on the of the entries on the off diagonal. So it's precisely this expression I've got in the text. By the way, there's a result that states for solutions to a linear homogeneous differential equation, the Wronskian of those solutions is non-zero if and only if y1 and y2 are linearly independent. In fact, we can generalize that statement and define Wronskians for higher order equations. And I think last time I may have mentioned, in fact, I mentioned just now that it's very easy to determine whether whether two solutions. In the case of a second order equation, it's very easy to determine whether or not they're linearly independent, right? I just said you look to see if one is a multiple of the other, but what happens if it's a sixth order or seventh order equation? We need 7 linearly independent solutions. Maybe that's not so easy to work out whether or not they're linearly independent. But it turns out we can use that result regarding the Wronskian. So for example, the third order case, the Wronskian is defined in this way. So, and the pattern generalizes to higher orders. So for the third order case, the Wronskian is just the determinant of a 3 by 3 matrix. So in the first row, we would place the 3 solutions, y1, y2, and y3. In the next row, we'd place their first derivatives, and then the next row, their second derivatives. And this pattern continues for higher order cases. Actually, we can talk about the Wronskian of functions, the Wronskian of 2 functions, or the Wronskian of 3 functions, and define it in this way. The result regarding linear independence is a little bit different. The result is simply stated, if the Wronskian is non-zero, then the functions are linearly independent. But when we're talking about solutions of a linear differential equation, a homogeneous linear differential equation, the statement is actually an if and only if. Anyway, that's a subtle point, but nevertheless, I thought I'd mention it, that this Wronskian is intimately related with linear independence of solutions of a linear homogeneous equation. All right, so going back to the second order case, if we have those 2 linearly independent solutions, y1 and y2, then what we can do is, for the particular solution, and this is where you can see it's very related to the reduction of order, or the principle behind reduction of order, where we have y1 and y2, and now we introduce these 2 functions, u and v, and set the particular solution to be u times y1 plus v times y2, and we substitute that into the differential equation, simplify things a little bit, and then see what comes out, and see if we can solve for those coefficients, or the functions u and v, right? We, for convenience, and this will become evident later, because what I'm going to do is actually go through this precise calculation. For convenience, we impose this second condition that u dashed y1 plus v dashed y2 equals 0. Now, I acknowledge at this stage that condition seems like I've plucked it out of thin air, which is true in some sense, but as I said, we'll go through and see where this condition appears. But really, what we're interested in is just having a solution to the differential equation. Now, if we've introduced 2 functions, u and v, in this case. So we've got 2 unknowns. You can think of it as having 2 unknowns. And we only really have one equation that we want to solve. So what we can do is impose any second equation that's going to make life easy for us. And then we have 2 equations and 2 unknowns, and hope that we can solve for those 2 unknowns. So that's the idea behind introducing a second equation, or by imposing a second equation like that. It's because we have 2 unknowns and only really one equation that we want to solve, or that we're interested in. Okay, so we've got a little bit of freedom to play around with those functions u and v that occur here. All right, so substituting that into the differential equation, into the left-hand side, imposing the condition that the ODE is satisfied, and this peculiar yet cunningly chosen second condition, right, this one here, right, we have 2 equations and 2 unknowns, and then we solve for u and v. And it turns out the result is that we end up with these nice integral formulae for those functions u and v. All right, now here, y1 and y2 are the the two homogeneous solutions, the linearly independent homogeneous solutions. R is the function that occurs on the right-hand side of the equation. So right up the top of the screen there, that's the ODE we started with. So that R is the R that appears in the integrand in both expressions. And the W appearing in the denominator is the Wronskian of those two solutions that I've just defined. Okay, so these are all the ingredients in the variation of parameters. So I think it's worthwhile now to have a look through that to work through that calculation and just see where these integral formulae come from. I will just make a note, though, before I go on, that in the textbook, Stewart, you'll find variation of parameters discussed on pages 1177 to 1179. All right, so that's what we'll do in this next page. We'll endeavour to derive those integral formulae. Just might make that slightly bigger. Okay, so that's what we're working towards, deriving these integral formulae for those coefficient functions u and v. All right, so once again, it's worth writing this down. The general solution is of the form yh plus yp, and we're going to assume that we have the form of yh is just this arbitrary linear combination of those two linearly independent solutions of the corresponding homogeneous equation y1 and y2. Okay, so we'll follow the procedure outlined on the previous page. We'll set the particular solution to be u times y1 plus v times y2. Now, just for the moment, I'm not going to impose this other condition. I'm not going to impose this second condition just yet, because I want you to fully appreciate how it simplifies the calculation. So I just want to proceed as if we didn't impose that, just to show you exactly how complicated it could be. All right, so the strategy here is to take this form of the particular solution and substitute it into the left-hand side of the differential equation. So remember, we'll use this form of the equation, so with coefficient functions p and q and r on the right-hand side. So to substitute this into the left-hand side of that equation, we need to work out the first and second derivatives. Now, we're assuming u and v are functions of the independent variable x. So I need to use the product rule in each of these terms. So that'll be u dashed y1 plus u y1 dashed for the derivative of that first term. And plus a similar pair of terms for v and y2 in place of u and y1. All right, and similarly for the second derivative, we'll end up with a few more terms. So again, differentiating each of these four terms using the product rule, we'll end up with a second derivative of u, and we'll also end up with a u dashed y1 dashed coming from the first term, and the same thing from the second term here. So we'll have two lots of u dashed y1 dashed, and finally a u times the second derivative of y1. So remember, y1 and y2 are solutions to the corresponding homogeneous equation. And so then we have pretty much the same thing, but with v and y2 in place of u and y1. So I'll just write that out for completeness. Okay, now we substitute that into the left-hand side of the differential equation. Now we've got, it's p, isn't it, times the first derivative. So the coefficient function p times the yp dash plus q times yp itself. Now what we might do here is just gather up all the terms involving u and its derivatives. So, and then do the same thing for v and its derivatives. So for example, if I'm taking yp double dash plus p times yp dashed, so that's the coefficient function p multiplying these four terms, plus q times these two terms. All right, I'm just taking the sum of all that. Now, you can see when I take that sum, there's only going to be one term involving the second derivative of u dashed. All right, but the first derivative, the second derivative of u. The first derivative of u, however, there are two terms. There's one coming from here, so I can write that as u dashed open bracket 2 times y1 dashed coming from this term, and then there's another u dash term, so that'll be a p times y1 here. Okay, remember I'm multiplying this coefficient p times the first derivative of yp. And then I've got three terms involving u, right? 1, 2, and 3. So I'll have y1 double dashed plus, and then there'll be a p times y1 dashed here, plus a q times y1. And then we'll have some very similar terms involving v and y2. All right? So I'll just quickly write those down without walking you through it. Plus v times y2 double dash plus p plus q y2. All right, now see those, I've written two lines here. See this last term in each line. And that's the term involving u and v. Now remember, y1 and y2 are both solutions of the corresponding homogeneous equation. Homogeneous, what does that mean again? Well, that means, going back to the ODE, that means the right-hand side is 0. All right, so that means y1 is a solution of the homogeneous equation, right? So when I substitute y1 into the left-hand side here, it vanishes. Now have a look at this expression, this coefficient of u here, those three terms. That's just the left-hand side of the differential equation with y1 substituted in for y. So since y1 is a solution of the homogeneous equation, those three terms vanish. They combine to give 0. And similarly for y2, so those three terms will vanish. Okay, so because y1 and y2 solve the corresponding homogeneous equation, we can do that. All right, so now here's where we go back to this condition that's mentioned on the previous page. The reason we can impose it is because we have this additional freedom. I remind you, we've got two unknowns here, the u and v. We've got two unknowns, but we're only really interested in solving one equation, namely the ODE. So we've got this freedom. We can impose a second equation that will allow us to solve for the two functions u and v. All I've got at this stage, the only equation I have at this stage is all of this. All of these terms equals the right-hand side. Okay, nothing more than that. So generally speaking, if I want to find a u and v that satisfies such an equation, that's going to be quite difficult. It's quite a mess in that case. But if I impose this other condition, so this one here, so u dashed y1 plus v dashed y2, so now I'm going to do that. U dash y1 plus v dash y2 equals 0. In fact, have a look at the expression I've got here for the first order derivative of yp. So u dashed y1 plus v dashed y2, they sum to 0. All right. So in fact, at that stage, if I impose that condition, I would have two terms rather than 4. Okay. So that would simplify this equation quite a lot. Because in fact, then when I go on to differentiate for the second derivative, I wouldn't have so many terms. In fact, we can work out if I differentiate this condition. So if I differentiate that condition, or differentiate both sides of this equation, I'd have u double dash y1 plus u dash y1 dash, and similar expression for v and y2 equals 0. Right? That's just differentiating the condition. All right, so you can see where this condition arises. So the coefficients of p here will have a u dashed y1 plus v dashed y2. So actually here, at this stage, we can start cancelling additional terms. Right? That is, terms in addition to these we've already cancelled. But okay, now we're also cancelling u double dash y1 plus one lot of u dash y1 dash. So I've got two lots here, so I'm really just cancelling that 2, turning that 2 into a 1, plus the v double dash y2 plus one lot of this v dash y2 dash coming from here. So those 4 terms there combine to give 0. Right? And so what are we left with once we impose that condition? Well, remember, it's only one lot of these 2 terms that vanished, and actually that's all that's left. There's nothing else. So all we're left with is the u dashed y1 dash coming from here plus v dashed y2 dash, which equals the right-hand side. We're setting equal to the right-hand side. So remember, this is really just this combination of yp and its derivatives with that additional condition imposed. So that's equal to the right-hand side, which is this function we're calling r. All right, so now we've got 2 equations. So here's the first one, and here's the second. All right, so once we impose that condition, that gives us one equation in our unknowns u and v, and then we've got this second equation. Okay, so we've got 2 equations and 2 unknowns. All right, so if I take equations 1 and 2, right, they're both linear equations, actually not in u and v, but they're linear in u dash and v dash. Right? So what I can do, I want to solve for u and v, so I guess at this stage I can try and solve equations 1 and 2 for the derivatives, u dash and v dash. So what I can do is actually put these, or write these as a matrix equation, so some 2 by 2 matrix multiplied by u dash v dash equals a column vector on the right-hand side. So let's just have a look. If I want to write those 2 linear equations in u dash and v dash as the unknowns, I want to write those 2 equations as a matrix equation. So just using matrix multiplication, the first row, so this first equation will correspond to the first row of this matrix equation. So I'll have u dashed times the first entry of the matrix plus v dash times the second entry. So I'll have y1 and y2 in the first row of that matrix, and then on the right-hand side I'll have 0 in the first entry. All right, so just using matrix multiplication, you multiply that out and you get the first equation. And then in the second row, we'll place the second equation. So that's u dashed y1 dash plus v dashed y2 dash equals r. Okay, so we've now got this matrix equation we want to solve for u dash and v dash. That 2 by 2 matrix looks familiar, doesn't it? The determinant of that is just the Wronskian, what I've written over up here on the previous page. And in fact, if you think about this result that I mentioned about linear independence, we're assuming that y1 and y2 are linearly independent. So that implies, right, from this if and only if statement, that implies that the Wronskian must be non-zero in this case. So it means the determinant of this matrix is non-zero. Think about what this equation looks like. It's a matrix A times some column vector V equals another vector W, right? That's this vector on the right-hand side. And what I could do in order to solve that, or in order to isolate this column vector with entries U dash, V dash, I could multiply both sides by the inverse of that matrix from the left. Right? Now, matrix multiplication, I'll have A inverse times A is just the identity matrix. So I'll be left with the column vector V on the left-hand side, and on the right I'll have A inverse W. So now the next question is, how can I invert that 2 by 2 matrix? I know the inverse exists because I know the determinant is non-zero, right? Because the determinant is the Wronskian, which is non-zero because y1 and y2 are linearly independent. We're assuming that. So that implies u dashed and v dashed is the inverse of that 2 by 2 matrix multiplied by that column vector. So there's a quick way of writing down the inverse of a 2 by 2 matrix. Does anyone know it off the top of their heads? Given those entries there, does anyone want to have a crack at it? Or? Yeah, well, yeah, that sounds like it, yeah. So let me just write that down. Actually, I think there's an easy way of remembering it. If you swap the entries on the diagonal, so here's the matrix. Now, if I swap the entries on the diagonal and then multiply the off-diagonal entries by -1, and divide through by the determinant, I'll have the inverse. But in this case, the determinant is the Wronskian. So actually, I can write it like that. Okay, you can check that. Just check to make sure I've got that right. And I mean, check for yourselves that when you multiply this matrix and this one, along with the 1 on W term, which is the determinant of the matrix, you end up with the identity. Okay, but anyway, now what we can do is just multiply everything out and see. So what's the first row? Remember, this is just scalar multiplication here, the 1 on W. So the first entry of this column vector on the right-hand side will have 0 times y2 dashed minus y2 times r. And we're dividing everything by the Wronskian. Okay. The second entry is just 0 times negative y1 dash plus y1 times r divided by the Wronskian. And then the result follows. Okay, so what result is that? Oh, that's the integral formulae given on the previous page. So we've worked out formulae for the derivatives of u and v. So now we integrate. Okay, so let's see how we can use that. How we can use this method, given that we've just derived the integral formulae. Alright, so actually before we leap into this method using variation of parameters, try and think of this. Imagine yourself sitting in a Math 2000 final exam at the end of semester, confronted by this example. And there's probably a process that you should be going through in your head now. When you look at these equations, you see this and you think, it's a second order equation. Oh, it's linear. Right, that's the sort of thing we've been doing in this course. Okay, good news so far. You're in the right exam. It's an equation with constant coefficients, right? So, okay, that's great too, because we can find the homogeneous solutions. All right, remember the general solution. Oh, and here's one mark in the exam, writing this down. The general solution is always this sum of these two terms, in this case, the YH plus YP. So because we've got constant coefficients in this on the left-hand side here, we can work out the homogeneous solution. All right, but so going back to project yourself into the future and looking at this, what method shall we use to find the particular solution? Okay, well, really there are a couple of methods now that we have at our disposal. We should be making an appropriate choice. So the method of undetermined coefficients is a good guess, is a method that makes an educated guess for the particular solution based on the form of the right-hand side. It works in the constant coefficient case and in the case where the right-hand side are polynomials, exponentials, cosine and sine functions, and products of exponentials and cosine and sine. Here we have a ratio. We have e to the 2x divided by sine x. So at this stage, I would have absolutely no idea what an appropriate guess for the particular solution would be in this case, right? So that's when I stop thinking about method of undetermined coefficients and then decide I'm going to apply variation of parameters instead. Okay, so just quickly for the homogeneous solution. For the homogeneous solution, we can see that assuming YH is of the form e to the lambda x, substituting that into the left-hand side, we end up with lambda squared minus 4 lambda plus 5 equals 0. Okay, so you can see plus 4 plus 1 equals 0, so that's lambda minus 2 squared plus 1 equals 0. So we have a complex conjugate pair for lambda, so that's 2 plus or minus I. So given that form, so that implies lambda is 2 plus or minus the imaginary unit. Alright, so from that I can straight away write down the form of this homogeneous solution. I'll have e to the 2x, because that's the real part of lambda is a 2, so that goes in the exponent. The imaginary part is just plus or minus 1, so I'll have cos x and then b e to the 2x sine x. Alright, so I'll call this guy y1. This function y2, they're clearly linearly independent, because if I take the ratio, say y2 divided by y1, I end up with tan x, not a constant. So for yp, we'll use variation of parameters, where u is negative 1 times the integral of y2 r on w, and v is the integral of y1 r on w, both with respect to x. Oh, and w is the determinant of that 2 by 2 matrix, the Wronskian. Alright, so in this case, the Wronskian works out to be, so y1 is just e to the 2x cos x. y2 dashed, we've got a product of functions, we'll have to use the product rule. So I'll have 2 times e to the 2x sine x plus e to the 2x cos x. And then I subtract from that the derivative of y1. Here's y1. So that'll be 2 e to the 2x cos x minus e to the 2x sine x multiplied by y2. Alright, so I've got these cos x sine x terms. So that term and that term actually cancel. And then I'm left with e to the 4x multiplied by cos squared x coming from here, and a sine squared x coming from the second term. Cos squared x plus sine squared x is 1. So that Wronskian just simplifies to e to the 4x. Okay, so we can then take this into our integral formulae for u and v. So y2 is e to the 2x sine x. We've got the function on the right-hand side, so this is what's written above, 2 times e to the 2x divided by sine x, so that's the r, and then the one on the Wronskian is 1 over e to the 4x. Oh, look at this. Look what happens in this example. The sine terms cancel, all the exponential terms cancel, and we're just left with integrating -2. So that's just -2x. I'll write it as -2x. And the coefficient function v, or sorry, the function v that we're looking for is y1. So integral of y1, which is e to the 2x cos x, multiplied by the function on the right-hand side, which is 2e to the 2x divided by sine x, and then divided by the Wronskian, or multiplied by 1 over e to the 4x. So we get the exponential terms cancelling in this case. So now we just have to integrate 2 times cos x over sine x, which is just 2 times the natural logarithm of sine x. So now I've worked out u and v. That implies that the particular solution is just u times y1. So that's -2x times e to the 2x cos x, plus v times y2. So that's plus 2 log of sine x times e to the 2x sine x. Okay, and remember the general solution is then yh plus yp, which you could then write down. Okay, so any questions about that calculation? I mean, if not, let me make an observation going back to what I said about making a good guess. Hopefully you can appreciate by looking at the form of the right-hand side here, it would be quite difficult to leap from that function on the right-hand side to guessing a particular solution of this form. Right, just point that out. Since no one's asked about it, I'll bring up a question. So when I evaluated these integrals, what about, I ignored the constants of integration. So I guess I can put, what about the constants of integration just in the evaluation of those integrals? Can anyone offer an explanation as to maybe why they're not so important? Yeah. Sorry, speak up a bit. Yeah. So yeah, think about where these functions are being placed, though. So so I think we're all on the right track here. So think about where these constants would be placed. So I'll say it like this: with the constants of integration, we would end up with a yp. So if I did put a constants of integration in here, when I come to writing down the particular solution, I would just have, I think this is what we were getting at before. We would have, so whatever this explicit function of x is for u, plus c1 times y1, plus whatever that other function is, the log of sine, plus c2, y2. And so you can see we've already worked out the homogeneous solution. So I guess the answer to that question is, what about the constants of integration? Well, all they're going to contribute to is are those arbitrary constants in the homogeneous solution. So in this method, the way I've presented it, it's not so important because we've already written down the homogeneous solution and stated right up the top that the general solution is YH plus YP. Okay, so I guess if you wanted to include the constants of integration, you could simply say our general solution then looks like this. Okay, but I don't know, something you should be aware of. Okay, so I guess they're the just 2 points I wanted to make is the fact that, well, now it looks like for this example it would be really hard to guess the form of the particular solution using the method of undetermined coefficients, and the constants of integration are not so important. So just those 2 subtle points. So once I wrote down the general solution, I took that form to MATLAB with arbitrary coefficients, and I just set different values for the coefficients just to see what the solution curves look like. And I got this nice pretty pattern. A set of points on the left-hand side, a set of points on the right, and all possible combinations between them done in this way. It seems like a bit of combinatorics that we're getting into. Anyway, some pretty pictures there for the solution curves. One more example and then we'll finish up. And I won't spend too long on this example because it's actually quite similar to the one we've just been through. Oh, this function on the right-hand side, the CSC, is it? I think it's just the it's the editor that or the package I used to produce this document, the maths package called LaTeX. Some of you might have come across this before, but this CSC is just the cosec function, the way it prints out the cosec function. So this is just 1 over the sine of 2x, right? So not the inverse function, but 1 over the sine. Okay, so since we're running out of time in the lecture, I'll just summarize this calculation. So remember the important points. We work out the homogeneous solution first. So you can see from the left-hand side, the characteristic equation is just going to be lambda squared plus 4 equals 0. So the values for our lambda are just going to be a complex conjugate pair with only pure imaginary parts, so plus or minus 2i. So just check then that the homogeneous solution is just, say, a cos 2x plus b sine 2x. And if we call this y1 and this y2, we end up with the Wronskian evaluating to 2. Right, a very simple form of the Wronskian in this case. And so the integral formulae, so negative y2 r on w, just evaluates. So I'm just summarizing here, okay? I'm not going to go through the details of the calculation. But this just evaluates to the coefficient function u works out to be negative 1/2, and v works out to be 1/4 of the log of sine 2x. And then the particular solution is uy1 plus vy2, as in the method that we've just been through, and this is negative 1/2 x cos 2x plus, so v times y2, that's 1/4 log of sine 2x times y2, which is just sine 2x. Okay, so actually comparing those 2 forms of the solution, oh yeah, maybe you can see a pattern. Maybe it is conceivable that we could put a bit of effort in to including these types of functions. So 1 over sine functions in a method of undetermined coefficients, but I certainly haven't presented it like this. Oh, and if you're curious, you might be wondering what the plot of this general solution looks like for a whole bunch of different different coefficients in the general solution, and it's a similar sort of pattern to the previous one. So look guys, on the next page is a summary of all the methods that we've covered and all the methods for solving differential equations that you should know about. So this one's the variation of parameters. See you tomorrow.